Well, good morning, everybody, and thank you very much. First of all, thank you to the organizers for giving me the opportunity to open this workshop and for inviting me to give this talk today. So I'm going to describe a bit the recent advances on indium phosphide integrated photonics for QKD applications, and also explain a little bit our work in the University of Vigo in our group. It's just we only have the summary is a bit short because we only have 20 minutes, so I'm going to go a bit fast through the slides. First of all, the problem that we are going to try to solve using integrated photonics is the well-known problem of the theoretically secure communication between a transmitter and a receiver. That is something that we all, as in the telecom engineering world, we all know also very well from radio frequency or fiber optics. And the idea is that there could be an eavesdropper in the middle, that is called E, that could record or attack either the transmitter or the receiver. So the only way to have secure proofs of this communication is that the key is as long as the message itself and can only be used once, and we cannot reuse that key. So that's the only way we can distribute that key. So this problem is what is called the key distribution problem. And nowadays it's being solved using different public key cryptography systems like AES or RSA or this type of systems. But these problems are usually based on computational assumptions, for instance, factoring large integers and so. But due to the recent advances also on quantum computers, these systems are no longer secure. So Alice, for instance, can copy the key during the distribution process, and once that we have a quantum computer, maybe in 3 years or 5 years or so, they could decrypt that key. So that could produce like a WikiLeaks for conversations made maybe 20 years ago. So the main goal of QKD is to have this security, but based on quantum mechanics laws of physics. There are 2 ways apart from QKD. There is another way to solve this quantum key distribution. This key distribution problem, and this is the post-quantum cryptography that is made on using conventional cryptography, public key cryptography systems, but using some encryption, symmetric encryption schemes that are known that quantum attacks do not apply to them. So it's an easy system to deploy, but it's not a theoretically or unconditionally secure system. So probably there will be a coexistence of both systems for some years. So this is, well, maybe I can go back to this. So there are 2 ways of doing this QKD distribution, the distribution of these keys. One is based on discrete variable protocols, a single photon distribution of this key, and it's based on encoding the polarization or phase of weak coherent pulses that simulate true single photons. This is what is called kittens, small bunches of photons or single photons. So we need to use single photon detection techniques like BB84. This is the best or well-known detection scheme or protocol for QKD, or the co-state BB84. We also have BB91, another protocol. And there are others based on photon arrival times or in the phase. The key is encoded in the phase between adjacent weak coherent pulses. So the problem here is that we need single photon detectors, and single photon detectors are expensive. We cannot integrate them at least very well. So there are many problems with discrete variable protocols in terms of having a complete integrated system. We also have continuous variable or CVQPD protocols where the information is encoded, in this case, in coherent states. So here we use homodyne or heterodyne detection techniques. So in this case, this is very well known for telecom engineers, and this is where we are basing our research in this field. So this approach offers the possibility for implementation based on well-known telecom components, off-the-shelf components. So all these protocols are what are called prepare and measure, because you produce the key and you distribute the key, and then the receiver just make the recovering of that key. There are other protocols that are called entanglement-based, where both parties receive part of an entangled state, and then there are another type of measurements involved. The performance of these systems is always distance over secret key. I mean, it's rate over distance. Now I'm going to describe more or less the state of the art in this, and then the third part of this presentation is based on what we are doing now. So these are different types of experiments made in optical setups. So a bit difficult, of course, to reproduce that, but this can be done without a problem. So here we have the single photon scheme, and here the continuous variable scheme. Here we have a BB84 protocol. This is a continuous CBQKD protocol, and this is the more or less until 2016 the performance of these systems. So based on these bulky experiments, the idea is that we want to develop an integrated photonics, completely integrated photonic system. So as we all know, chip integrations produce a compact, lightweight modules, mass manufacturing at low cost. We can include in some platforms electronics and post-processing. The problem is that if we want to develop QKD protocols, that there are a lot of them, we need to select discrete variable, continuous variable, and then we need to focus on the detection, because as I explained, if you use single photon detection for discrete variables, there is a really enormous complexity on the receiver side. If we go to off-the-shelf components using continuous variable QKD, this is more adequate for metropolitan areas, but not for hundreds or up to thousands of kilometers using discrete variables. Besides that, we need to select the integration platform. So we can go to silicon, indium phosphide, or alternative techniques like lithium niobate, glass waveguide, diamonds, many other systems. So what is the state of the art now in integrated photonics for distributing key, using this key, using quantum mechanics for producing this key? So here you can see this is a transceiver that has been made in 2019. Many of these platforms are using now silicon or silicon nitride, but the most recent advances are progressing through indium phosphide. So this is a transceiver. Here you can see a high-dimensional quantum key distribution system, or even WDM using multi-core fibers. And here you can see a CBQKD system. Also, these are from a couple of years ago. Most of them you will see that are Chinese developments, because they are, as you know, they are producing a huge network, both on fiber optics and also on satellites. So they are producing a lot of circuits and systems complete for these networks. Apart from BB84, the problem with quantum key distribution is that this is like a paranoid security implementations, because in the end you need to know, to be secure, that the receiver is completely, you can trust on the receiver side, you can trust on the transmitter, you need to trust on all the chips that are inside the electronics or your devices. So there is a protocol that has been in 2012 invented by Foy Kwon Lo, Marcos Curti, and Vinci, I think. And this is called measurement device independent protocol, where you have, instead of having a transmitter and a receiver, you have two transmitters. And these two transmitters make the same transmission to the receiver, and then later, when the receiver produces gives back the basis where he has received that information. It's a protocol based on BB84 actually. There are some correlations that both transmitters exchange between them. So even if the receiver is untrusted, you don't need to trust on the receiver, but still you have secure communication. So if you go back to what I explained before, there is a transmitter and a receiver. So this is only for point-to-point networks. But in this case, if we have two transmitter and a receiver, but I don't trust the receiver, I can do a star system. So I am moving from a point-to-point network to a star network. And this is a big advance because you can transmit using a star. This is the first type of network that is different from a point-to-point. And apart from that, I don't need to trust in the receiver. So that's very good. So we are moving to having secure proofs that we don't need to trust the receiver, parts of the transmitter, parts of the receiver. So based on this MDI, you can see here also MDI QKD based on silicon photonics, and here also a QKD based also on silicon photonics. But here we have in 2020 the first MDI QKD system based on indium phosphide, made by the group of Chris Erben and David also here. And you can see that still we need single photon detectors on the other side due to the complexity of detecting single photon. But this is the as far as I know, the MDI QKD system based on indium phosphide. There are other implementations or peak implementations in indium phosphide. This is, for instance, different or reconfigurable QKD system that can admit several protocols. For instance, the co-state BB84, distributed phase shift protocols. So it can be used for different applications. And this is a system that does not need a quantum random number generator because it's based on a master laser and a slave laser. So there is the slave laser, the master laser produces random phases in the cavity using a switching mechanism, and then it carves that random phase into the slave laser. So this randomness in the phase is internally produced in the chip, so you don't need a quantum random number generator to produce random phases or even random amplitudes into the chip. And for all of these systems, except the last that I mentioned, you need a quantum random number generator because the idea is that you produce a pulse and you make a modulation of the phase and the amplitude of those pulses, and then you need to randomly select between a variety of amplitudes and phases, and then transmit it in constellations, for instance, for continuous variable QKD. So there are several attempts to produce quantum random number generators. This is a very well-known chip that has been produced here in Spain. It's a company, QSite, that is implementing these quantum random number generators. But there are other attempts or other implementations also well-known. So there are several of them. But this is just an example of 3 of them that have been implemented in indium phosphide. So just going a part of explaining this state of the art, as you can see that apart from silicon, that is a well-established and known platform in indium phosphide, there are many implementations that are now underway. So there will be a lot of them because we can select a different variety of protocols, devices, What we're trying to do now in the University of Vigo, in my group, that is the Antennas and Optical Communication group, is to develop our own QPD, CVQPD platform. So we have here a continuous variable QPD system that actually is a continuous wave laser, amplitude modulator, phase modulator, several variable attenuators, because here in the end we want to produce a really weak coherent pulse around 10 photons per symbol. Here we have an homodyne detection system that is being used for control of this constellation. This actually is a QPSK constellation. And here we have a quantum random number generator. This should be a fiber optic 40-kilometer system, and then here a receiver. The receiver is also again an homodyne detection system. The difficulty here is just to produce something that is quite stable, really low noise, that you can control low power. Here you should need to mix the local oscillator for any type of this coherent detection systems. A local oscillator that is high power mixed with the quantum signal that enters into the receiver that is less than 1 photon per symbol. So this is a very difficult process to be implemented in indium phosphide. Right. So we started with the transmitter, and now we based our research on this article here that has been produced in 2011. So we did this design that is a DVR laser. This has been implemented in the Smart Photonics platform. This is a DVR laser. Then we have a Mach-Zehnder interferometer to control the power that goes into 2 arms of an asymmetric Mach-Zehnder interferometer. And what we have produced here is a short pulse. So we can produce a random phase in that pulse. Then we switch it off. We empty completely the cavity and produce a new pulse with new and random phase that is completely uncorrelated with the previous pulse. And so we convert we transform that random phase in this asymmetric Mach-Zehnder interferometer into a 1-bit delay. So we collide both pulses, the one with the previous one, and we transfer that random phase into a random amplitude. So we are producing random amplitude pulses, and this is a quantum random number generator, at least theoretically. So this is the schematic of the chip that we produced. And so we measured the results. We have published the results of this chip. I don't know if we can see something here, because I'm afraid that we cannot see the video. No. Mouse. Yes. Mouse. Yeah. So you can see this is the raw key that is going out in the photodetector. So we are producing random amplitude pulses going out of this transmitter. So the result is that we have a 1.8 gigahertz rate for these random pulses, but this is a raw key, so we need to make later some post-processing. There is a post-processing mechanism that is also well known, so we need to make an analysis of the decimal sequence, later conversion to binary with 16 bits or more, random next extraction and statistical analysis. So we extract the autocorrelation coefficients from these pulses, Gaussian distribution by graphical and quantitative means, and then we pass several tests, statistical tests. This is the NIST, the statistical test suite, but also like the die-hard test suites, to confirm that the quantum random number generator actually is random, that in the end is random. So you can see here that the autocorrelation coefficients are lower than 10 to the -2, and that it passes the NIST test. So we have patented this chip. We have the national and international patent for this chip. So now we have the quantum random number generator. We are going through the CVQKD. So we have here the schematic of this chip also. And the chip is, again, the laser, the amplitude and phase modulator. Here we should have the quantum random number generator that should rule these amplitude modulators and phase modulators and select with these random bits, one random amplitude and one random phase. Then we attenuate around 100 and, if I remember correctly, 117 dBs, and then we are producing here 10 photons. We also transmit the local oscillator, and we mix that signal here with the local oscillator and make a no-modine detection just to control these modulations here. This is just a control system. So this is the layout for this chip. This is made in DPI. This has been sent to HHI platform. This is the chip. This is the result of our chip here. And this is right now the measurements are also ongoing measurements. We have the last, actually this week. This is part of a PhD thesis from one of our students. So this should be ready this week. We have applied for a national patent, and now we are going for the international patent again for the CVQT mechanism. And I'm strictly adhering to the schedule. So this is what we are doing now. So right now, what we are going to develop is the receiver. So for that, we will probably use silicon nitride, because we think that is right now is not possible to develop that in indium phosphide. But we are developing in indium phosphide other different applications for quantum technologies. Like, for instance, we have prepared and submitted to one to a smart photonics platform and another one to HHI, a dual optical classical and QKD modulator feed transmitter, an OCDMA implementation for a classical and QKD transmitter, physical and clonable function units, like in this case optical fingerprinting for some modules. So we are continuing with these quantum applications. As we all know, QKD is a pre-commercial technology. So it's probably between the 4 different technologies in quantum that we have: quantum communication, computation, simulation, and sensing. This is probably the most mature system or application. So we think that we are on the verge of producing a lot of devices, new protocols where all the telecom engineers, like one of them, and we can also provide some expertise coming from networks, coming from the telecom world to the physics world, in this case, in this type of devices. So this is the team part of the team that has been produced this chip. So these are some of our PhD working there actually in the Netherlands. And this is all. It's mainly a state of the art and a description of the systems we are producing with indium phosphide devices. Now, thank you very much.
Thank you very much, Frank. Now let's start for questions. Questions here in the room.
Thank you very much for this talk. And I think you mentioned that you are using DDR lasers to generate pulses. That's full gain switching.
Yes.
And what is the advantage over, for example, networking?
with mode locking, initially it could be a good idea to use mode locking mechanism or frequency counts, for instance, for those systems, because you could multiply by a lot the number of random bits that you are producing at the same time. So why you are asking why we didn't use? Well, because at that time we wanted to try DVR lasers, because when we started with this idea, there were no DVR or gratings in the smart photonics platforms. We also did it by ourselves. I mean, we did the design of the gratings and submitted also.
Because
No, initially DFB lasers for that. I mean, we could use a DFB laser or a mode lock laser, and that would be great.
and the characteristics line width of the laser and these characteristics of the lasers, do they matter?
Yes, initially the DF, in this case for the quantum random number generator, the line width should be really, really short. So in that sense, DFB lasers should be.
Thank you very much.
Any other question? Any question? Okay, thank you very much.
Thank you.